All right, so our marshmallows have sat out overnight. Actually, I did wrap them in saran wrap. I didn't want them to get too dry, number one, and number two, I didn't want them to attract any ants, okay? Because it is spring and they are starting to come in when the kids leave the doors open, etc. So in order to slice these, I need a knife, of course. All right, so as you can see, somebody sliced some of these last night. I shared some with my family, and I came back and the slice was here. And then when I came back later, this whole column was gone. Turns out my wife likes marshmallows. Who would have known? Okay. All right, so I'm just putting a little bit of vegetable oil. This is actually avocado oil on my knife so it doesn't stick too much. And that will allow me to cut right through here like this. And it's okay to recoat that. It's okay if it does stick a little bit. It won't hurt too much. Okay. And then once you have them in about 1-inch cubes or so, you can pull them out. The sides will be sticky. You can coat them. This is a mix. If you have powdered sugar, that's perfect. It's probably all you need. A lot of times, if you look at a marshmallow bag, it will say tapioca starch or cornstarch or potato starch along with it. So this is a nice starch coating, so it doesn't, they don't stick to each other in my container here. And there you go. You can see it. They don't stick because it is kind of sticky on this exposed side there. So I'm just going to do that with a couple of them here so we can get started, and then I'll do the rest on my own here. You guys, so roll that in there, take it off, put it in your container. And you can be as thorough, perfect as you want. Now, our next phase, what I wanted to do with these today was put them in, well, the original idea was to put them in the microwave, but I have no microwave anymore. And so I tried putting them in that convention toaster oven because you have a really nice light on it, hoping that the heat would cause some expansion in there. But I don't know if they were too fresh and so they didn't expand. But I will do it really quickly just to see if anything happens. And if something does happen, I'll record it for you. But if nothing happens, I won't record it. So I guess what I should do before I do that is the one that did work. So these are nice and light and airy, meaning that there's lots of air bubbles trapped in them. And what we're going to affect right now is the air bubbles. So there's a couple laws in chemistry that deal with the pressure and volume. It's the first one we're going to look at. And there's one that deals with heat and volume. That's the one I was hoping to show you. But I guess we'll just have to do it a little more generically. Have you do it at home or just try to remember. So hold this thought. Okay, so pressure and volume, right? So this, there are some air trapped, and of course if I push pressure on this, it will reduce in volume. So that's pretty obvious. Now, there is one little thing I want to just briefly mention as a side note. These sugar crystals that were in my maple syrup did not totally dissolve, right? And there are 3 ways to make things dissolve better, and I don't think I've actually mentioned them all. I've mentioned heat, so we can have heat help aid in reactions and dissolution. But grinding it into a powder or pulverizing it, making it powder, that's the second thing. And then stirring, right? And so a lot of these ones I was constantly stirring. So movement, stirring, basically powdering, pulverizing, it increases the surface area in which reactions can take place. And again, heat can add energy to help overcome those barriers, that activation energy, so to speak. That's the name for that. So again, I was going to try to put these in a heat source to heat them up to show you that, but let's do the next best thing with pressure, which is a vacuum. So I need to pull a small bit off of one of these. If you have mini marshmallows, okay, let's do it this way. If we were in the classroom right now, we would have mini marshmallows. Not my homemade ones. And we would put them in this tube. And I forgot to do something, or I did something too early. It was really hard to squeeze that down in there. All right, so put the cap on too early. Okay, so there you go. You can see the marshmallow. I have a darker surface here. Okay, so you can see the marshmallow there. Figure 1. It's about the same. It's the same at the doctor, I swear, my doctor. And when I pull back on the plunger, okay, see that again. So it's starting off here around the 15 milliliter mark. Shake it down to the in there. And when I pull back on the plunger, it is growing. It's growing. Okay, why? What's going on? Well, those atoms, those gas molecules, are moving around inside the marshmallow. They're trapped in by the gelatin, but they're still moving. Okay? That's something to remember. Gas is still moving. It's always moving. All atoms are moving, for that matter. But the gas molecules trapped in by that gelatin are moving. And there's also gas molecules on the outside of this marshmallow that are still moving. And when I either force the marshmallows on, sorry, getting distracted here, force the molecules on the outside of the marshmallow to be confined to one space. Now, I'm not actually squishing the marshmallow right now, but I'm condensing the amount of volume that those gas molecules that are trapped in there as well are taking, and those are pushing on the marshmallow. So it's not the plunger as much as the air that's causing a lot of that reduction in size. Now, some of it is because it shifted a little bit, but it's mostly the air molecules. And so again, if I give them more room, there are fewer air molecules striking the side there, which allow the marshmallow to expand because the air molecules on the inside of the marshmallow are pushing outward on it. Okay, so here we go. And that's pressure versus volume. Which is also known as Boyle's Law. And so we studied him a long time ago when we talked about the periodic table, or the history, foundations of chemistry, we talked about Boyle. And that's what one of the laws he was known for. If we put this in a microwave, I am confident it would expand because microwaves work a little different. They will excite the water molecules specifically, cause them to vibrate quickly, right? And of course, that affects temperature. And so that increased temperature causes the water to vaporize and turn to steam. And that steam takes up much more space than the gas, right? And so you have volume and temperature there. That's Charles' law. Okay. And then lastly, pressure and volume can also affect. Okay. I said that yet? Okay. No, that was the first one. That was Boyle's law, right? Pressure and volume, Boyle's. Okay. Volume and temperature is Charles, and then pressure and temperature. If you spray a can of condensed air, you'll notice it gets very cold, and that's a good example of that, right? The reduction in pressure reduces the temperature. Okay, so that is Gay-Lussac law, and we can put it all together. If we know pressure and volume, if we know and volume and pressure, if we know temperature and volume, temperature and pressure, we can find the third one if we know how much matter we have, because they're all interrelated with gases. So that's called ideal gas law, right? So there's just a little glimpse of gas law chemistry there with our marshmallows. And then tomorrow we'll hopefully have a little better weather. I haven't gotten my stuff for making chocolate yet, so we'll throw the Mentos and Coke in there, and then we'll do the chocolate on Friday. Okay. Take the quiz, and we'll see you tomorrow.